Good afternoon, welcome everybody. We have another of our weekly seminars hosted by the Simons Bootstrap collaboration. Just a small announcement, next week we will have David Meltzer tell us about the recent work on the O2 model. And today we're very happy to have Kurt Hinterbichler from Case Western speak about unitarization in Kaluza Klein theory and the geometric bootstrap. Thank you.
Okay, thank you very much for the invitation. So I'm going to be talking about these two papers here, and my collaborator is James Bonifacio. He's one of our postdocs at Case Western, and he's here as well in the audience. And he really deserves most of the credit for everything that I'm going to talk about. He's the one who really figured out how to implement this bootstrap and do all the numerics and everything. So the starting point of all this is, let's see, how do I? Don't seem to be able to go to the next slide. Okay. So the starting point for this is we were interested in the question of scattering of massive higher spin particles. So this is this PDF is not working. Let me go back to the keynote. Okay, so the starting point of this was we were asking about effective field theories of massive high spin particles and the question of whether you could unitarize them at tree level through Higgs-like mechanisms. So the standard example of this is in the standard model. If I look at just the effective field theory that's governing the massive spin ones in the standard model, the W and the Z bosons, if I look at the tree level scattering of longitudinal modes of W and Z scattering, they grow with energy, like energy squared, which means that they violate perturbative unitarity at some energy scale. So in the standard model, that's the TeV scale. This was the no-lose theorem for the Large Hadron Collider, that something has to happen at that energy scale. Some new physics has to kick in to restore the perturbative unitarity. So we can ask the same question for other field theories. In the case of spin 1, however, we know that there's a solution. There's a solution where we can remain weakly coupled by just adding in a new field. So we can add in the Higgs, just a new massive scalar field. And when you add this new massive scalar field and you include it in the intermediate states, and all of a sudden the high energy bad behavior is canceled off, and you just get a constant amplitude at high energies, which restores perturbative unitarity as long as the couplings are low. So we succeed in getting a weakly coupled UV completion if we do this.
Okay, we're just looking at your title page still.
Oh, no. Okay. How do we? Sharing is paused. Bring your shared window to the front. How do we do this?
It seemed to be working earlier when we tried.
Yeah, it worked fine when we tried. Let me try again. Okay, does that work? Okay, do you see a non-title page?
Yeah.
Okay. Okay, so here was the Higgs mechanism in the standard model where we add a new scalar in the middle. It still says paused. Why is this paused? Hmm.
You're unable to change slides?
Yeah, it says that sharing is paused and nothing happens when I click resume share. Okay, I may. Try one more thing. Okay, let me just try like this. Do you see this?
We do.
Okay, and you see when I change the slides?
Yes. Maybe this.
Okay, all right, I'll just do this. Okay, so here's the standard model. Here's the Higgs in the middle restoring unitarity. We can ask the same question now about massive spin 2s or higher spins. So massive spin 2, it's been of interest because that's a theory of massive gravity. If we look at a generic effective field theory of a massive spin 2, so generic interactions like Einstein-Hilbert plus some potential for the graviton, generically these amplitudes will grow with energy like 10 powers of energy, so violates unitarity very quickly. There are special choices of this potential you can make, which can improve this. It can make the growth slow down to energy to the sixth. That goes under the name of DRGT, massive gravity, which has been of recent interest the last 10 years or so. But it turns out that this is the best you can do, no matter what interactions you choose, whether they're Einstein-Hilbert or not, as long as there's some finite number of interactions and you only have a massive spin 2, the best you can do is this energy to the sixth behavior. So we have an argument about that in this paper here. You can then ask about the Higgs mechanism. Is it possible that there's a true gravitational Higgs mechanism for gravity, in the sense that I start with some massive graviton and then I add in a finite number of new lower spin particles, spin 1 and spin 0, analogous to some Higgs, which then improves the behavior to some power that's less than 6? And the answer to this is also no. You can show that no matter how many particles you add in, as long as there's a finite number, if they're of low spin, no matter what the couplings are, you can never improve the behavior past this energy to the sixth point. So there's no true Higgs mechanism for gravity in this sense.
A question?
Yeah.
Can you give a little bit intuition about why you cannot go past e to the 6 by adding a Higgs mechanism?
Yeah, I don't really have a good intuition for that. It seems to be a natural boundary, and this, which doesn't exist for spin 1, but also exists for any spin higher than 2. There's this boundary that it seems to be a boundary beyond which you can't go with local finite number of interactions, but I don't have a good intuition for why it's at that point.
Yeah, I mean, it seems bizarre that this happens for spin 1, but doesn't happen for spin 2. That's why.
Yeah, it's one of these spin 2 barrier things. Like gravity is harder. Okay, but we know that there's loopholes to this if you allow for an infinite number of particles. So one loophole we know is string theory. If you have an infinite towers of massive higher spins, you can unitarize the spin 2s that are in there. But also, even with sticking to spin 2 or lower, Kaluza Klein theory, if I have Kaluza Klein theory, that should also be able to do better by having infinite towers of massive spin 2s in the spectrum. So let's look at a Kaluza Klein theory where we start with some pure GR in higher dimensions, and then we reduce it on some smooth n-dimensional compact manifold. So we'll get some theory in lower dimensions that has the infinite towers of Kaluza Klein modes coming from reducing on our n-dimensional compact manifold. And now we know that the higher dimensional theory is just pure general relativity. So we know that amplitudes in general relativity grow like energy squared. The lower dimensional theory, if we keep all of the Kaluza Klein modes, then that should be nothing but a rewriting of the higher dimensional theory. So that should also have amplitudes that grow like energy squared. So even if I look at amplitudes with external massive spin 2s in the Kaluza Klein theory, they should somehow be able to go past this energy to the sixth barrier that we have for effective field theories of massive spin 2 and be able to get all the way up to energy squared. So by including all of the Kaluza Klein states as intermediate states in the Feynman diagrams of an external massive spin 2 scattering, we should be able to see a cancellation that gets you to energy squared that requires all of these infinite modes in the Kaluza Klein tower. So our goal is to understand exactly the mechanism for this cancellation. How does this cancellation occur in general? And that's going to lead us to this bootstrap. Okay, so let's look in more detail at the Kaluza Klein reduction. So we're starting with the higher dimensional Einstein's equations, which tell us that the internal manifold has to be an Einstein manifold. So the equations of motion enforce that on the background. And this is going to give us all the non-trivial juice that allows us to say things about eigenvalue spectra and so on. We wouldn't be able to do anything if we didn't have this Einstein condition. We want to understand what the lower dimensional spectrum is in general. So the lower dimensional spectrum is going to be determined by various Laplacians on the internal manifold and the eigenvalues of the eigenfunctions of these Laplacians. So we'll need to have three different Laplacians. We'll need the scalar Laplacian, the vector Laplacian, and a spin 2, a tensor Laplacian. So let's review what those Laplacians are and how their eigenvalues behave. So we start with the ordinary scalar Laplacian. So this is just the ordinary del squared. So the eigenvalue spectrum here we're calling lambda sub little a, which little a will index the eigenvalues. So they're all positive. So we're not going to be including the zero mode in the index little a. They satisfy orthogonality when we integrate over the manifold. And there's completeness. So any scalar function phi I can write as a linear combination of the eigenmodes and a zero mode. So V here is just the volume of the internal manifold, which is gives you this properly normalized zero mode. There is a special value for these scalars, which go by the name of conformal scalars, which satisfy this double derivative equation here. And these exist only on the round sphere. So that's a kind of special case we only need to worry about for spheres. And there's a bound, the Lechnerowitz bound, which tells us that the eigenvalues, the lowest eigenvalue is bounded by the curvature over dimension -1, and this bound is saturated only for these conformal scalars.
Sorry, n is the dimension of the Einstein manifold?
Yes, n is the dimension of our internal manifold, which is Einstein. Okay, next we need the vector Laplacian, which is just the Hodge Laplacian on one forms. So we're going to be looking only at transverse vectors. So we're on the space of transverse vectors. And the eigenvalues are going to be labeled by this lambda little I, and they're always positive. They are orthonormal. And there's a completeness relation, which says that any vector can be written as a linear combination of the transverse vectors and longitudinal vectors, which are just derivatives of the scalar eigenfunctions. There's a special value for the transverse vectors, which are the killing vectors, which satisfy the killing equations. So those are there if you have isometries of the internal manifold. And there's a bound which says that the eigenvalues have to be greater than 2 times the curvature over n, and this bound is saturated only by the killing vectors. So if you have negative curvature, then the fact that they're all positive kicks in, and this bound, you can never saturate this bound. That's why you don't have any killing vectors on negatively curved compact manifolds. Okay, next we need the tensor Laplacian, or the Lechnerowitz Laplacian. So that's this combination here. So lambda squiggly I is going to denote the eigenvalues of the Lechnerowitz Laplacian. So we're looking only at the space now of transverse traceless tensors. These are orthogonal as well, orthonormal. And there's a completeness relation, which is like a Hodge decomposition for symmetric tensors, which tells us that any symmetric tensor can be written as a linear combination of the transverse traceless ones plus longitudinal things, which are derivatives of the vector the Laplacian eigenmodes, plus transverse stuff, which is derivatives of the scalar eigenmodes, plus trace stuff, which can be written as the scalar eigenmodes. And there's a special value of the Lechnerowitz Laplacian, which are what we might call the zero modes, which correspond to the moduli space of Einstein structures, the different ways you can deform the metric while retaining the Einstein condition. These are going to lead to massless scalars in the lower dimension. And in general, there's no lower bound that's known in general for the Lichnerowitz Laplacian. So in general, there could be some finite number of negative eigenvalues on any given manifold.
There are examples like that?
There are examples. So we're going to be mostly looking at Ricci flat manifolds, and in that case, I don't know any examples, but it's not been proved that there aren't any, as far as I'm aware.
But is there any example if you relax the Ricci flat condition, or?
That I'm not sure. Maybe James, do you know?
Yeah, there's these bow metrics, for example.
Okay. And those are negative. Are those positively curved?
Those are positively curved, yeah.
Okay, there you go.
All right, what were those called?
Bohm metrics?
Bohm, BOHM.
Okay, so when we do the Kaluza Klein reduction, so we take the metric and we expand it in fluctuations around our background, and the fluctuations we expand into the lower dimensional and higher dimensional parts. So MN are the little m and n are the indices on our internal manifold, mu, nu are the indices on our large dimensions. And each of these parts we now expand over the eigenvalues. So we get different coefficients now, which are fields on the lower dimensions. So the blue fields you see here are like actual physical fields that we're going to get. And the red fields end up being pure gauge things that are like longitudinal parts of the other fields. So this h mu nu here, these are going to be the tower of massive tensors. And these massive tensors have longitudinal modes, so they basically eat these other parts here. And here's our massless tensor, and we're going to have a tower of massive scalars, which eats this scalar, and then there's going to be two towers of other massless scalars, which correspond to these Lichnerowitz eigenmodes and trace-like modes. Okay, so at the end of the day, this is what the actual physical spectrum looks like. So our lower dimensional theory in general has always a single massless graviton corresponding to the zero mode of the scalar Laplacian, a tower of massive gravitons whose masses correspond to the eigenvalues of the scalar Laplacian. There's a tower of massive vectors. I think there's some feedback. Maybe some people can mute. So there's a tower of massive vectors whose masses correspond to the eigenvalues of the vector Laplacian, and these vectors become massless only when they're killing vectors. Then we have two different towers of scalars. We have one tower of scalars which corresponds to the, whose eigenvalues correspond to the scalar Laplacian again. This comes from basically trace stuff. And the zero mode of this is what we call the volume modulus. And then there's another tower of massive scalars which correspond to the Lichnerowitz eigenvalues. And this becomes massless when the Lichnerowitz eigenvalues are the shape moduli, so the Einstein structure moduli. Okay, so we're mostly going to be interested in the flat
cases. Sorry, in those special cases where you have a negative, then you'll have tachyons.
Exactly, yeah. Okay, so we're mostly going to be interested in the flat space spectrum. So we want to do S matrix stuff. So we want our internal manifold to be flat, which implies that we want our external manifold to be flat, which implies that the internal manifold also has to be flat. So it has to be Ricci flat. The closed Ricci flat manifolds are actually rather rare. There's only a finite list of known examples. So we have tori, we have the Calabi-Yaos, we have some special cases, G2 spin 7. And all of these have special holonomy, which by a theorem of Yau says that the Lichnerowitz eigenmodes all have to be greater than or equal to 0. So if we look at what the spectrum is expected to be in general, so here's the spin 2 modes. They're all positive mass except for a massless one at spin, which is the massless graviton. Here's our spin 1 tower, which are all massive except possibly if you have killing vectors, some of them can be massless. And then here's our two spin zero towers. We have our ones corresponding to the trace stuff, where you have the volume modulus at the bottom, that's massless. And then you have the Lichnerowitz tower. And if you have Einstein structure moduli, those are massless, but it's possible that you could have tachyons. So the only way you'd have tachyons, which would be an unstable flat compactification, is if there were some undiscovered Ricci flat manifold that wasn't in this list of cases here that had negative eigenvalues for the Lichnerowitz. So it's still not known whether all Ricci flat manifolds have this positivity condition or not. Okay, so now we look at our amplitude, our scattering amplitude for the massive spin 2. So all the external things here are some massive spin 2 within that massive spin 2 tower. And now, if we include everything in that Kaluza Klein tower, so all the various towers in the intermediate states, along with whatever contact interaction comes out of the theory, this amplitude we expect to behave better. There should be magical cancellations that happen. So in order to compute this, we need the various cubic vertices that appear here and this 4-point contact vertex. So if we look at these cubic vertices, here is the cubic vertex for 3 different massive spin 2s within the massive spin 2 tower. And this cubic vertex is going to be proportional to a triple overlap integral of 3 of the scalar eigenfunctions. Here's the cubic vertex between 2 massive spin 2s and the massless graviton. There's no free coefficients there. That's going to be fixed basically by minimal coupling. Here is cubic interactions between the massive spin 2 and the massive vector tower. That's going to be proportional to this triple overlap between 2 scalar eigenfunctions, one of the vector eigenfunctions, and one insertion of a derivative here. Here's the interactions between massive spin 2 and the first scalar massive tower. That's again proportional to triple overlap of 3 of these scalar eigenfunctions. And then finally, we have cubic vertices between the massive spin 2 and the Lichnerowitz tower of scalars, which is proportional to this triple overlap between 2 scalar eigenfunctions and a Lichnerowitz eigenfunction with 2 derivative insertions. And you can check that these all have the correct symmetry properties and so on for the type of vertex they are. We also need the quartet contact interaction, which is going to be proportional to a quadruple overlap integral of 4 of these Lichnerowitz, 4 of these scalar eigenfunctions. Okay, so now we have everything we need to just compute this amplitude. So when we compute it, we're going to get some expression that has powers of energy going all the way up to energy to the 10th. That's the naive behavior that you'd expect for a massive graviton, with some coefficients out front. So these coefficients alpha are some mess that depends on all the various cubic couplings and scattering angle theta and so on. And what we expect is that all of these coefficients, alpha 10, 8, 6, and 4, all have to independently vanish because the result has to go like energy squared, which we expect from the high energy theory. Okay, so let's look at how this cancellation has to take place. So if we look at the alpha to the 10th cancellation, for example, this is the expression that we get. So this is now an expression that relates the quadruple overlap to the triple overlap integrals. So this is now an expression that just has to be a true geometric property about the internal manifold. This makes no reference to physics or anything. This is just a mathematical property of the internal manifold that now has to be satisfied. So where does this property come from? Well, if we look at a product of any 2 eigenfunctions, so this product here of 2 scalar eigenfunctions, this is again some scalar function, so it should be expandable as a product of the scalar eigenfunctions by using completeness. So when we write this expansion, the coefficient here is going to be nothing but the triple overlap integral, which you find by multiplying by another scalar here and integrating and using completeness. And so this you can think of as kind of like an operator product expansion, if you like, for the eigenfunctions. I can always take any 2 eigenfunctions within a multiple overlap integral, and I can use completeness to replace it with a sum of single eigenfunctions. So any multi-overlap integral, any n-point integral, if you like, I can always reduce down to 3-point integrals by using over and over this completeness relation. But if we have a, say, a quadruple overlap integral like this, there's multiple ways that you can use the completion relation. So there has to be some associativity condition or a crossing relation, if you like, that has to be satisfied. So for this quadruple overlap, I can use completeness in 3 different ways, using all the different ways of pairing up the 2 fields denoted by these Witt contractions here. So there's 3 different ways to do it with 4 fields, and that gives me these 3 different expressions in the sum rule, and you can show that this sum rule literally follows directly from this crossing relation. So this crossing relation is what causes the coefficient alpha 10 to vanish. If we look at the sum rule now at the order e to the 8th, so the next subleading part that has to vanish, we get this expression here, which depends on some of the various triple overlaps and the eigenfunctions. And this, you can show, comes from a similar crossing relation where we now have some derivatives inserted into the crossing relation. So if you evaluate this and use the completeness, so for example, for this one here, you'd have to use the completeness relation for vectors because you've got this derivative making a vector index here. But if you work that all out and reduce it, it reproduces this first line here. And this expression now has some non-trivial consequence for the eigenspectrum. So if I look at the second term here, this second term has to be positive because the eigenfunctions are positive, which means that this first sum here has to be negative so that I can cancel off and sum to 0. So there has to be some contribution within this sum here, which is negative. And since g squared, the cubic coefficients are all real, so g squared is positive, means this coefficient here has to be negative. So that means for any given external flavor that I'm considering for a massive spin 2, there has to exist some other a here within the sum, some other state in the Kaluza Klein tower, such that this coefficient here is negative. So there has to be some other lambda which is greater than 4/3 of the lambda that I'm scattering, which means that there has to exist another exchanged particle with a mass that's greater than 2/√3 of the mass of the external particle. So there has to be some heavier particle that's present of whichever other one that I'm scattering. And now if I go back and I scatter that heavier one, there has to be a heavier one still, and I repeat this ad infinitum, and that tells me there has to be an infinite tower there. So this is another proof, if you like, that there's an infinite number of eigenfunctions. And it's also proof that you need to have this infinite tower in order to get the right cancellation of high energy behavior. Okay, now if we go down to energy to the 6th, here's the expression we get. And again, this comes from some crossing relation that now has 4 derivatives inserted. Going down to e to the 4th, here's the relation we get. And this now comes from some crossing relation which has 6 derivatives inserted. So this is the last one that has to cancel since we expect the amplitude to go like e squared. So let's look more closely at this crossing relation. So now we're going to make an assumption that these Lichnerowitz eigenvalues are always greater than 0, which was true for all the known cases. So this is basically the assumption that this Kaluza Klein compactification is stable. If we make this assumption, then this second term again is always positive, which means that this first term here, there's this polynomial here as that depends on x, which is just the ratio of eigenvalues here. This first term also has to be negative. And so for any particle that I'm scattering, there has to be another particle whose mass or eigenfunction satisfies this bound here. So this tells us that for any given particle I'm scattering, there has to be another one within this ratio of 4. So any given eigenfunction, there has to be another eigenfunction whose ratio with the first one is never greater than 4. So this gives us a bound on the gaps between Kaluza Klein excitations of the graviton. Nowhere in the spectrum can there be a gap that's larger than this. So in particular, this tells you that you can't really make out of a Kaluza Klein theory like this a effective field theory that has a finite number of massive spin 2s, a finite number of massive gravitons. Because to make an effective field theory with a finite number of massive gravitons, I need there to be a parametrically large gap in the spectrum so that I can integrate out massive stuff and be left with just some finite number of modes with some parametrically controllable gap that will set the scale of the effective field theory. So this says you never have that. And this is now just a generic fact about eigenfunctions of closed Ricci-flat manifolds. And as far as we know, this was not known to mathematicians beforehand, that there's this condition on the spectrum. And it applies to any manifold that's Ricci-flat that satisfies this positivity condition. So in particular, it'll apply to all smooth Calabi-Yau compactifications of string theory or supergravity or M theory or whatever.
Sorry, this is a theorem. You didn't use any physics to prove this.
That's right. That's right. You can consider this just a purely mathematical result that follows from this associativity of the multiple overlap integrals.
What about the e to the 6 sum rule?
That didn't give us anything that's stronger than this.
Do you have any kinds of bounds on the triple overlaps?
Yes, I'll show you some of those later once we get to the numerical stuff. Okay, so this is what you might call the first kind of bootstrap constraint that comes from this associativity condition. So it bounds the gaps between the eigenfunctions. And we know also that this bound is optimal. So there are various tori that saturate this bound. So you can't improve this. Here's a non-trivial example. So the quintic Calabi-Yau manifold, you can't calculate the eigenfunctions of this exactly, but numerically these people have computed the low-lying eigenspectrum, and here are the eigenfunctions, the eigenvalues rather, as a multiple of the volume. And indeed, they satisfy this bound up to their numerical errors. And the Einstein condition is essential for having this bound. So there's this funny theorem. If I have just a generic Riemannian manifold, not necessarily an Einstein manifold, if you give me any closed Riemannian manifold and any finite sequence of non-decreasing positive numbers, any sequence of k numbers, then I can find a metric on that manifold such that the sequence is precisely the first k eigenvalues. So without the Einstein condition, with just a generic Riemannian manifold, you can basically get whatever spectrum you want. So there can be no such interesting constraints like this. So if we were doing Yang-Mills theory instead of gravity, we wouldn't have this constraint. So gravity is somehow special for this.
I guess the Einstein but not Ricci-flat case, well, you'll get to that too.
Yeah. So we'll relax that in a second. Okay, so there's an analogy between all this and what CFT bootstrap people do. So we can think, if you like, of these eigenfunctions as like primary operators of a CFT. We can think of the eigenvalues as like the scaling dimensions of a CFT. We can think of these multiple overlap integrals as like correlators of a CFT that we're trying to compute. The covariant derivatives that we've saw inserted in here, we can think of as like descendant operators of a CFT. This completeness relation that we use, we can think of as like the operator product expansion of a CFT. The various sum rules that we saw are necessary for the correct behavior of the Kaluza Klein theory. These are like crossing relations for CFT correlators. The various bounds that we had on the eigenfunctions, like the Lishnerowitz bound, these you can think of as like unitarity bounds. And now we can think of geometric data. So if I think of the eigenfunctions, if I think of the eigenvalues and the triple overlaps, these are like geometric data, a set of numbers that's associated with any manifold. And that's kind of like the CFT data. So in the geometry case, if I give you this geometry data, you can then compute any of the multiple overlap integrals by using the completeness relation. So in some sense, the geometry data tells you everything you need to know about all the multiple overlaps, just like the CFT data tells you everything you need to know about all of the correlators. What we'd like to know, so in the CFT case, we know that the CFT data essentially defines the CFT. If I have some set of CFT data consistent with crossing relations, then that's kind of defines a CFT and uniquely comes from a CFT. we don't know if that's true for the geometry data. So what we'd like to know is if I give you some geometry, a set of geometry data that's consistent with the crossing conditions, does that actually uniquely come from some manifold? Does it uniquely specify a manifold? So we know that the eigenvalues alone don't do that, because there are isospectral manifolds. There are you can't hear the shape of a drum, but maybe if you include the triple overlaps, maybe you can hear the shape then. We don't know if that's true or not. That's something we'd like to know.
So
a question which I guess
isn't there a theorem to that effect, that if you do include the triple overlaps and the geometry is specified, isn't this?
Is it? I don't know. We couldn't find any theorem of that kind, but would be. Have you heard of something like that?
Well, I may be mistaken. I thought it was a theorem. It follows from the non-commutative geometry context. I think it's true, and I think in the classical limit. But.
Okay, yeah, we'd be interested if you knew any, because we couldn't find anything of it to this effect.
Regarding your third line,
yeah,
of course, I like the analogy, but of course, on the CFT side, we consider correlators, which are functions of positions, which we can dial, which is different from a full overlap integral over all space. Is there anything you can do to, I mean, does it make sense to generalize that in the manifold side, or?
I don't know. Yeah, I don't know. Like in some sense, this is like a zero-dimensional CFT. It's like a CFT without position. So I don't know. Maybe there's some sense in which if you consider some moduli space of manifolds, you could consider the moduli as positions or something. But I don't know.
It's a bit more like topological quantum field theory.
That's right. Yeah. Okay, so what we're going to try to do is set up a numerical bootstrap in analogy with the CFT bootstrap, try to exploit these crossing relations to constrain the geometric data, just like the CFT people do. So we're going to take some set of these crossing conditions. So here are the various crossing conditions that we had at the various orders in energy in the Kaluza Klein reduction. But now we can just forget about the Kaluza Klein theory. We can just consider this a mathematical exercise on some closed manifold, and we can relax the Ricci flat condition. So we'll allow some general Einstein space now. And when we evaluate these crossing conditions, we'll get some more complicated expressions. So those complicated expressions, we can always package them as some vector equation like this. So these f's here are just some vectors of numbers that depend on the eigenvalue data and so on. And this condition always has to be true, this vector equation. So now we can kind of set this up as a bootstrap problem. So we postulate some candidate geometric data, some candidate collection of eigenvalues and triple overlap integrals. And then we search for some constant vector alpha, such that when we dot it into our equation that's true is equal to 0, we search for some alpha such that this can never be satisfied by our candidate data. And if we can find such an alpha, then we've ruled out that candidate data. And the problem of finding such an alpha, this can be formulated as a semi-definite programming problem, and we can solve it using the same kinds of numerical semi-definite program solver that the Bootstrap people use, or even Mathematica in some of the simpler cases. Okay, so now I'll show you some plots, some results from this numerical evaluation of these things, which put bounds on this geometric data, bounds on the various eigenfunctions first, and then I'll show you some bounds on the triple overlaps. So here's a plot of an upper bound on the ratio of the two lowest lying eigenfunctions. So lambda a2 over lambda a1, the y-axis here is this ratio of the two lowest lying eigenfunctions. And I'm going to show you as a function of the Lichnerowitz eigenvalue, normalized by the lowest eigenfunction. So we're making here the assumption that the curvature is greater than or equal to 0. So this dotted line here, this is the ratio of 4, the bound that we had earlier in the Ricci flat case. But now when we use this more complicated bootstrap, we improve the bound. So we get a little bit below that. So the various lines here are just the various dimensions of internal manifold. And these points down here are some actual examples that we can explicitly calculate. So real projective space and complex projective space, and we'll show you the spheres later. So we get an interesting kink here, just like the conformal bootstrap people do. We don't know if there's anything interesting happening at that kink or whether it's just an artifact, but we'd like to know if there's any interesting manifolds that we don't know about at that kink. So there's very few manifolds where we can actually calculate the eigenfunctions explicitly. Basically, it's just the spheres, the tori, and projective spaces, and that's it.
It's curious that that kink is very sharp already for n equal to 2. I mean, in bootstrap studies, what typically happens at the kink starts smooth and then it gets sharper. I mean, is there some obvious reason why the kink should be there even from the get-go?
No. So in the CFT case, where when you say it starts smooth and gets sharper, what parameter is being dialed there?
N is the dimension of the manifold, right?
Oh, N is the dimension.
Yeah, N is the dimension. So yeah, there's nothing really fundamentally different, I guess, about.
Sorry, I thought this was.
It's not precision improving or anything.
I thought it was precision. I'm sorry.
No.
Excuse me. May I ask how's N entering the bootstrap equations? At which point N enters?
So when you evaluate these completeness relations, there's various places where metrics get contracted with each other, and you get powers of N.
And I have another question. The plots look like just a junction of two straight lines. Maybe it's possible that instead of numeric analysis, one can analytically see what those two lines are?
Yeah, it's possible. We didn't have any analytic thing that gave this, but it's if these are indeed optimal. We don't even know if these are optimal or not, but if they are, then indeed, yeah, there should be some analytic thing to get this. Yeah, so we can check in a few cases that we satisfy the bounds in manifolds that we can actually compute. So you can think of like the spheres and tori as like analogous to free CFTs where you can actually compute stuff, but we'd like to know if there's like a strongly coupled manifold, if you like, where you can't actually compute the eigenfunctions that maybe live at these kinks.
Can I ask, is there an analog of the derivative order for this plot? Is there some parameter that you had to increase in order to get these curves, or are the curves just from some fixed semi-definite program?
Well, I think you do have to, these completeness relations involve infinite sums, so you do have to truncate it at some point. So there's an analog for that.
Okay, and what kind of truncation are you choosing for this plot?
James, do you know?
No, so there's no truncation.
Okay.
The derivative order is basically fixed to be at most 6 derivatives in these integrands, and that's something that we don't know how to improve upon systematically. It seems like that's the end of the road.
You said n minus 6?
Sorry, 6 derivatives for any n.
Okay, I see. So you're just considering all the crossing equations that you can get by sticking derivatives in everywhere. And
yeah.
There are always 6 of them.
There are always 6 derivatives, and that only gives you 3 sum rules. Yeah.
Yeah, we don't know how to go beyond 6 because there's going to be powers of the Riemann tensor that enter that you can't deal with by using the Einstein condition.
Great, thanks. That helps a lot.
Yeah.
But if you made some stronger assumption, for example, that the metric is locally hyperbolic or something like that.
Yeah, indeed. Yeah, then we could go further, but then we don't know if there's, yeah, so indeed, if you made the assumption that it's maximally symmetric locally, then you could presumably go to all orders. Okay, so here's now the same plot, but now we're making an additional assumption, which is a Z2 symmetry under which the lowest eigenfunction is odd. So this is like the L equals 1 spherical harmonics, for example. And when we make this assumption, we get a little bit stronger constraint. The kink moves a little bit. The bounds are no longer straight lines. And we saturate them here for the spheres. So these dots are the spheres. Here's another way of visualizing the 2 lowest lying eigenvalues. So here's a plot now for positive curvature manifolds. So the curvature is positive, and we're looking at the lowest lying and second lowest lying eigenvalues normalized by the curvature in a plane. So we've picked a particular dimension here, n equals 4. So this blue region is now the region which is allowed. And if we make certain assumptions on the third eigenvalue and the Lichnerowitz eigenvalue, then the sphere appears here at this kink. So we've kind of tuned things here so that the sphere appears at the boundary, but the fact that it appears at the kink is non-trivial. Here's complex projective space, which appears near the boundary, which makes us think that this is nearly an optimal bound. And then there's this other kink here, and we have no idea if any manifold actually appears at this other kink.
So why did you make these assumptions about lambda A3 and lambda I?
This was just to get the sphere to the boundary, basically.
Oh, I see.
Yeah, so it's kind of fake that the sphere here appears at the boundary, but the fact that it's at a kink and not just some generic point at the boundary is still non-trivial. Okay, here's some bounds on the next higher eigenvalue. So here we're looking at the ratio of the third eigenvalue to the first eigenvalue as a function of the second eigenvalue to the first eigenvalue. So we get some complicated looking curves here. So these dotted lines we're not using any kind of symmetry condition on these triple overlaps, but if we assume some certain symmetry conditions, we can get those improved to these solid lines. And below here, this purple, funny looking purple region is the entire moduli space of flat two-dimensional tori. So we can check that all the possible tori appear below the bound as it should for n equals 2. And here's the Fermat quintic also appearing below the bound for n equals 6. Here's some bounds now on triple overlap integrals, on cubic couplings, if you like. So here we're looking at upper bounds on the lightest possible, the cubic coupling of the lightest possible massive Kaluza Klein state of the spin 2. So the self-coupling of the first massive spin 2 normalized to the volume. So as a function of dimension here, these blue dots are the numerical upper bounds we find. And these other shapes here on the bottom are various cases where we can compute explicitly the cubic couplings and check that they're below the bound. So here again, we've made some assumptions that the curvature is positive and that the Lichnerowitz eigenspectrum is positive. Here's some more cubic couplings. So here's, again, we're looking at the cubic couplings of the first non-zero eigenmode of the spin 2. And now we're looking at the cubic coupling as a function of the ratio of the first two eigenvalues. So we see now that as you make this ratio go to its maximum value, so we saw that the ratio could never be larger than 4. As you make the ratio approach 4, the cubic coupling has to go to 0. So as you make the ratio as wide as possible, the cubic coupling has to turn off. And that's saturated by the tori where this cubic coupling vanishes. Here's now a funny looking plot that we get when we look at the cubic couplings between two different Kaluza Klein modes. So now we're looking at the cubic coupling between the lowest lying Kaluza Klein mode and the next lowest lying Kaluza Klein mode. Again, normalized to the volume as a function of the ratio of the two eigenvalues. So we get these funny looking shapes, which we get a funny looking shape only up to this dimension 12 or whatever it is, and beyond that it just looks like straight lines, and we don't know why this is happening. This just comes out of the numerics. But we can check in all the cases where we can actually compute these triple overlaps, we can check that they satisfy the bounds. Now here again is the same plot, the same cubic overlap between the two lightest Kaluza Klein modes, but now with this additional Z2 symmetry assumption, so we can get stronger bounds. And now we're close to optimal because we have spheres that are saturating these bounds. Okay, so this is just a sampling of these various plots. So if you look at our paper, we have many more plots of this type with various other cubic couplings between the other Kaluza Klein towers and various other eigenvalue plots and so on. And there's much more that could be done. We just did a bunch that we thought were interesting, but there's many more that could be done using the same techniques. So I'll summarize. So we found new non-trivial constraints on the possible eigenvalue spectra and triple overlap integrals of Einstein manifolds. So as far as we know, these constraints that we're getting by considering these multiple overlaps in the crossing are not known to mathematicians. We couldn't find anything about considering these things. They come from these crossing relations on multiple overlaps, and these are the crossing relations that ensure that the correct high energy behavior of Kaluza Klein reductions occurs when you're studying gravity. So our main open questions are, we want to know if we look at these kinks that we have in the bootstrap bounds, are there actually manifolds that live there? Can you isolate those manifolds? So we weren't able to do anything that could actually isolate into an island anything. So like in the conformal bootstrap, we know that non-trivial CFTs like the Ising model, at first they were seen to live at kinks, but then as they considered correlators between different operators, and they were able to isolate that kink into an island. We haven't been able to isolate any islands yet, but we'd like to know if there exist any manifolds or whether this could be used as a way to compute spectra. So the only way to compute spectra is now what you might call the analog to a Monte Carlo method, where you pick some specific manifold and you numerically try to find the metric and compute the eigenvalues like they did for that Calabi-Yau. We'd like to know mathematically if a manifold is uniquely determined by its geometric data. So is it possible that there are two manifolds that have the same, that are different, that are not isometric to each other, but have the same geometric data, or can they truly be distinguished? And alternately, is it possible that there's geometric data that's consistent, so satisfies the crossing relations, but does not correspond to any manifold? So that would also be interesting, because that would be a way to rigorously define what you mean by a non-geometric Kaluza Klein compactification. If you had some data that was consistent, satisfied these crossings, but didn't actually come from a manifold, you could still do a Kaluza Klein theory. You would still have all the correct behavior of the Kaluza Klein amplitudes. So that we'd like to know that as well. Okay, so I'll finish there, and thank you.
Thank you very much. So we have time for questions.
I have a question about these three overlap integrals. Is there a name in the mathematics literature about what these things are called?
Not that I know of.
So they're like sort of brand new kind of invariants, if you like, in some sense.
No, they're not. They're not.
I mean,
I will refer you to the book by Kohn on non-commutative geometry.
Okay.
So I'm trying to look for the theorem, but I might be totally confused. But I was under the impression that there was precisely a construction theorem.
Okay, because I know he considers things like spectral triples and so on, which.
That's right.
But that's completely different.
So perhaps I'm confused. It's entirely possible I'm confused.
So there was a paper by Bajas and Estes, I believe, from some time ago, where they write the massive spin 2 spectrum in terms of a warp factor in a solution of 10D supergravity. So your solutions can be translated into some constraints on the possible warp factors. Is that something you thought about?
Yeah, not directly, because we're assuming there's no warp factor in all of this. So, but I imagine you could generalize it.
To
include
are you assuming that? Yeah, how exactly are you assuming that? I thought you were just solving a geometric problem. And
well, like if the constraints they are getting, are they coming from like physics considerations of the string theory on this warp space?
Excuse me, they're just rewriting the 10D supergravity equations compactified on this space-time and then extracting the Laplace equation for the massive spin 2 modes.
Okay, but that Laplace equation, does it have like warp factor? It must have warp factors in it or something.
Yeah, it has a warp factor in it, but it ends up being, yeah. So I guess, are you saying that?
So you'd be learning about the spectrum of the warped Laplacian or something.
Yeah, I guess maybe I'll turn it around. So if we're trying to apply your conclusions to Kaluza Klein compactifications to lower dimensional CFTs, are you saying that they would only apply to direct product solutions of, say, supergravity?
Yeah, directly, but I'm sure we could generalize to include like warped Laplacians and so on. But the constraints could be different.
Yeah, another natural generalization would be to ADS compactifications.
Well, I mean, that's sort of included here in the sense that.
Yeah, that's included as long as it's a direct product.
But I have a question about this. If you consider the case where the compact manifold has positive curvature, then you can have ADS crossed at compact manifold. And then the dictionary you have, it seems to me, is the standard ADS-CFT dictionary, where from the eigenvalues you get the masses, and then the masses correspond to the dimensions of the dual operators. That the triple overlaps give the 3-point functions using the usual ADS-CFT dictionary.
Yeah.
If you take that on part and if you look at the graphs, then they should correspond to actual CFTs.
Yeah, yeah, good, yeah.
Have you done that comparison to see whether, in a sense, your kinks or?
Yeah, no, I mean, because the only cases where you actually kind of know what the CFT is are also cases where you can just compute explicitly the spectrum of the internal manifold. So to do this, we'd like there to be some example of a compactification on some non-trivial manifold where we don't know the spectra, but we do know the CFT, and then we could compare.
But you can get from your kinks, in a sense, the dimensions of, once you know the masses, you know what is the dimension of the compactification manifold. So
yeah,
then you can use the usual formula to get dimensions of the dual CFT, and then.
Right, but how would we know there's like an actual CFT that realizes those, or would we?
Well, I guess it's saying you have a prediction.
That's the usual, in a sense, ADS-CFT. Maybe not all of them are realized, but you can check whether what you get is in the list of known CFTs.
Yeah, I guess we could check whether they're consistent with CFT bootstrap bounds as well.
Yes, yes.
Yeah. Okay.
But the best you could do with that is getting functions of D.
You don't have position dependent, so it's some integrated version, if at all.
Yeah, but through
ADS, this is just like the reducing over the S5 in ADS5 cross S5. You get the spectrum, and you know the dimensions just from the spectrum of type 2B on S5.
Yeah.
And then you also from the reduction you get the couplings of in 5 dimensions and so on. I think it's the analog of the S5 in the ADS5.
Yes, but I'm saying that the bootstrap constraints that he has are some vastly simplified version of the bootstrap constraint you get for the boundary series.
Yeah, sure.
One small obstruction to going further is that you actually don't know the dimensionality of the CFT because no one told you from the beginning what the higher dimensional theory is. If they just tell you the dimension of the compact manifold, then you don't know what D is for the CFT. So
you can start from either either in 10 or 11 dimensions. So.
You could. But yeah, it's up to you. I guess you could say it more optimistically that you get dimensions and couplings as functions of D possible space-time dimension of the CFT.
Any further questions?
I have one.
Yeah.
So can you say a bit more about the cases where you have a sort of a truncation of your analog of operators? So there is the guy, which is the conformal scalars, which truncates to second order. Can you understand higher truncations, and do you have any sort of interpretation of those? The
sorry,
conformal scalars, for example, in ADS compactification are related to sort of singleton modes that you can get in ADS. Are they higher truncations?
I'm sorry, I wasn't. Yeah, I'm not aware of that. You said the conformal scalars are singletons, are related to
They're
singletons.
related to the singleton modes. So if you take, for example,
Because I thought
type to be on S5, you get the singletons in the spectrum. Those are related to the presence of conformal scalar.
Oh, that's interesting. Okay, I didn't know that. I thought the conformal scalars were just not part of the spectrum, because at least locally you can gauge some way, but you're saying they're singletons, which are
for the scalars. For the scalars themselves, it is not. But if you think about the actual spin-2 field that would eat such a scalar, so that would be missing. So actually, the spin-2 field would be partially massive.
No, I don't think that's true. It's not true. Yeah, there's no partially massless mode. I think one of the scalar towers goes missing, not the longitudinal mode.
So one of the scalar towers goes missing. So that would be removed from what an analogous spin-2 field in the bulk that would be massive. That's the question that I'm asking.
Yeah, no, there are no partially massless modes in the bulk. So when that conformal scalar is being removed, it gets removed from the scalar tower, not from the longitudinal mode of the massive graviton.
Okay. But so the question, however, still, if you have these internal manifold, is there higher truncations that you can think about?
Yeah, that's an interesting question. So, but is there anything beyond? I thought singletons were the only unitary thing you could have that's like that. If you try to go to higher things, are they still unitary?
Well, that's partially why I'm asking whether there are higher modes that you can obtain, because so the conformal scalar gives you singleton, but can you see anything else?
Yeah. Okay. That's an interesting question.
May I also ask a question about the torus? What is, if you assume that your manifold is a torus, how do you see that from the spectrum?
How do you see the torus? So, I mean, you just see the right eigenfunctions of the torus appearing in this spectrum. So you can calculate exactly what the spectrum of the torus is. And you'd see
on your exclusion plots, the torus is always sitting at the kink of some sort?
Yeah, the torus, or at least, so these are the tori which always saturate this bound that we've had. So this bound of 4 for the ratio of eigenfunctions. So these are those specific tori.
I was just curious, is it possible to restrict the search in your Bootstrap space to the symmetric manifolds? I assume that you have some group acting on the manifold and it's a symmetric space. And
yeah, that would be possible. So that would come as restrictions on what these various 3-point functions could be.
So maybe then you can reduce everything to representation theory, and I'm just guessing. Maybe all the kinks you see, you will be able to understand them from this representation theory point of view.
Yeah, that might be possible. Our hope would be that it's not that it's actually some interesting manifold that's not interesting just because of higher symmetry.
So I understand that from the point of view of Kaluza Klein theory, it's very natural to restrict to scalar, vector, and tensor Laplacian. But as a mathematical problem, is there any information in the higher tensorial Laplacians or the higher form Laplacians?
Yeah, that's good. Yeah, so that's something we need. So right, so this analogy I made to CFTs isn't quite work yet because this completeness relation isn't quite it doesn't quite close yet. So for example, if I take two of these tensor eigenfunctions and I try to expand them, I would need like a spin 4 basis of eigenfunctions and so on.
Who can stop it? Who can stop it? You can just, I mean.
Well, we don't know how to define on a general Einstein space like a higher spin Laplacian. So we could do it on a maximally symmetric space like a sphere, but we can't on a general Einstein space. If you tried to write like a spin 4 Leshnerowitz Laplacian, it wouldn't play nicely with the other Laplacians. You'd get Riemann tensors and stuff and the commutators, and so we don't know how to do that. And that's analogous to this, to the massive higher spin barrier, or massless higher spin barrier. Like on a free CFT, I can have these higher spin conserved currents and so on. And a sphere is like a free manifold, if you like, where you can have these higher spin Laplacians. But on a general manifold, we don't know how to define those.
Any other questions?
Sorry, one more question. So if you impose the conformal killing condition, do you actually see that you can only get spheres from your Bootstrap equation?
No, not directly. So we don't really impose that anywhere in the actual Bootstrap.
Because that's like removing a null state.
Yeah. So that would, I'm not sure how you'd want to enforce that one of the modes is at that value. But that's an interesting question.
Because then you could ask, similar to Leonardo's question, if you have some sort of things that truncate at higher order, do they sort of classify a set of manifold? Or what happens if you, for example, take products of spheres, where you can have different types of these null states?
Right. Yeah. So. Yeah, that's an interesting question.
Okay.
Do you know?
So, yes, sorry.
Do you know anything about how these overlap integrals behave under, say, isomorphisms or anything of that sort?
Yeah, they transform. I mean, as rank 3 tensors under any groups that you might have.
They're essentially nice to deal with, right?
Yeah.
Is there any information about the signs of these triple overlaps?
I don't think the sign is meaningful because I can always redefine the eigenfunctions with a minus sign to flip it.
But once you fix some conventions, then comparing different ones, doesn't this become meaningful?
Let's see. Yeah. Okay. Yeah, maybe. Yeah, we haven't thought about that. Does that happen in CFT?
Well, I think the sign of OP coefficients is of some interest depending on the application.
Okay.
Could you use the extremal functional method here and read more eigenvalues in the boundaries, I mean, of the region?
Yeah, you could, but I guess the abstraction there is basically plotting it.
We also might not have enough sum rules to do that effectively, because we have at most 14.
Yeah, just because we're limited to how many derivatives we can insert. But we could still presumably get more than we can plot.
Okay, so if there are no further questions, we can thank Kurt for a very nice talk, and we'll see you next week.
Thank you.